Hello everyone, in this video I want to talk about molecular polarity. Alright, now what does that mean? That means that molecules have a plus and a minus end to them. So the molecules that you're looking at right here on the left, they are sharing electrons. All of these molecules are sharing electrons, but if the molecules are not sharing them equally, then there's more charge on one end than the other because the electrons are not distributed equally. All right, for example, in HCl here, it has a plus and a minus end to it, a plus and a minus end to it. And we can indicate that with this little Greek letter delta that says delta plus and delta minus, and it shows the plus end on there. All right, so that's what polar molecules are about. Now, what determines whether they share electrons equally or not is a property called electronegativity, which is a general attraction for electrons. All right, now each element on the periodic table has a different electronegativity, and we do have a trend for this that we didn't talk about back when we did that, but in the upper right-hand corner, fluorine has the most electronegativity. All right, the reason is it has very little shielding effect, and it attracts electrons the most. All right, it attracts electrons the most. And then down in the opposite corner is the one with the least amount of electronegativity. So as far as the trend goes, electronegativity increases when you go across and decreases when you go down. All right, but we're not going to worry about trends at this point on that. Note that on the noble gases are white here, indicating that they have an octet, and therefore they don't really attract electrons to make bonds. All right, so this whole business, electronegativity, is only something we consider when it makes a bond. All right, when it makes a bond. So it's going to talk about how the electrons are actually shared, and since noble gases don't make bonds, we don't assign them a value for electronegativity. All right, now when does electrons actually transfer as opposed to being shared? All right, that is, when do you have an ionic bond as opposed to a covalent bond? Well, that depends on the difference in electronegativity for each element. If they have a large difference, then one element attracts electrons a lot more than the other, then the bond becomes ionic. If they both attract equally, then we say it's a nonpolar covalent bond. All right, now, at this chart, then this kind of tells us, what type of bond would happen depending upon their difference in electronegativity. All right, so when is it ionic? When is it covalent? It's not always perfectly well defined on there, but if the electronegativity is large, then it's probably going to be ionic, and we'll give this number 2.3 as a value for the difference in electronegativity. Looking at this chart right here, this is a table of electronegativities, at least for the alkali metals, alkaline earth metals, and the noble and the non-metals, as well as noble gases. The electronegativity of all the transition metals are pretty close to the same thing, and they usually always make ionic bonds anyway, so this only applies to covalent bonds. So we assign a number to electronegativity to each element, and fluorine we're going to give the highest number. All right, so we're just going to arbitrarily say, well, let's say fluorine has 4 as a number, and everything else then could be compared to that. All right, so then if something has less, then its number is less than 4. All right, notice in the lower left, then the smallest number, at least on this chart, is 0.7. So that tells us how how the electrons are shared. If the element is very electronegative like fluorine, then it will pull the electrons more toward that element than the other. So if you were to hook up, say, francium and fluorine together, then fluorine would practically steal the electron francium, and it would probably be an ionic bond. All right, so now looking at this chart then, if we compare the electronegativity of any two elements, we'll determine whether it's going to be ionic or not. If their difference is greater than 2.3, then the electron just transfers and it's an ionic bond. And then opposites attract and you get an ionic compound. All right, if the difference in electronegativity is not very big, for example, between nitrogen and oxygen, all right, let me get rid of all this writing here. The difference is only 0.5, all right? So they're almost the same. So if nitrogen and oxygen were to connect together, they would almost share electrons equally. Oxygen would pull the electrons toward itself a little bit more than the nitrogen, and it would be slightly polar. So if the difference is anywhere between 0 and 2.3, then we're going to say that that bond is polar. The electrons are not shared equally. If there is no difference in electronegativity, then of course both atoms are going to share electrons equally, and it won't be polar at all. It won't have a plus or a minus end at all. All right. All right. Remember we talked about the Brinkelhoffs, those diatomic molecules that bond with each other, two atoms of the same element. Well, their electronegativities between the two of them would be exactly the same. Therefore, there's not going to be any polarity at all for those molecules. They won't have a plus and a minus end at all on there. All right. Most elements, when combined together, are going to have some kind of polarity. It might be very slight. The only time you'd get perfectly zero difference would be if two atoms of the same element are hooked together. All right. Now, we could kind of illustrate this with some kind of a diagram here. For example, if H and Cl hook together, hydrogen chloride, that's the hydrochloric acid that we talked about a little bit later. Because chlorine is a little bit more electronegative, it's a value of 3, than hydrogen having a value of 2.1. The difference is 0.9, and it fits somewhere in between 0 and 2.3. So HCl is a polar molecule. It has a plus end and a minus end to it. And then that will give rise to some properties which we'll talk about a little bit later. Okay, so question. Which of the following pairs is the most polar? Now, what do? You have to look up their electronegativity. So for C, it's 2.5, and all of these have C in it. And then we have N, which has 3.0. That difference is 0.5. Between C and H is 2.1, and that difference is 0.4. C and O is 2.5 and 3.5. That difference is 1. And C and BR is 2.8, so that difference is only 0.2. So the most polar bond of all these molecules right here would be the CN molecule. The CN molecule has the biggest difference in electronegativity, so that would be the most polar. All of them are going to be somewhat polar as well. In fact, we might even say, well, none of these is going to actually be as far as being ionic. Now, what do we call this when the electrons are not shared? We call that a dipole. All right, di meaning two, and poles are like the plus and minus. All right, so if two atoms are not sharing electrons equally, they will create a dipole, all right, in between them. So, for example, in this molecule right here, which is water, H2O, the bonds here are not, they're slightly polar, and the hydrogen will has less electronegativity than oxygen, so the oxygen will pull the electrons toward itself more, and this bond here then is considered to be a dipole. All right, that makes the whole molecule be a dipole as well. So here's kind of the whole molecule of water, and this side of it is plus, and this side of it is minus. So water is what we call a polar molecule. It has a plus and a minus end to it, and that gives rise to a lot of the properties that water has. Okay, what is the partial charge of each of these molecules? Draw the dipole moment. All right, now if I draw a dipole moment, what I'm drawing is this arrow. All right, and the arrow points from the plus side to the minus side, and then we kind of put a plus there to indicate which end is the plus. All right, now in the case of two elements that are the same, the dipole moment would be 0, because they both have the same electronegativity and they are going to share electrons equally. All right, for the other ones, we'd have to, if we want to determine which one has the greater dipole moment, we will have to have that chart of electronegativity so that we can have something to measure. All right, so between O and F, the difference is 0.5. All right, so 0.5 for this one. So it has a dipole moment. All right, let's look at the second one. F and I is 2.5 and F is 4, so that difference is 1.5. So the dipole moment would be greater. Now, which direction will it point? All right, it's going to point toward the higher electronegative one. So fluorine it's going to point this way. Fluorine is the most electronegative, and the other one will point this way, like that. And then we could put a little plus sign indicating stuff like that on there. Now, if we were drawing them comparatively, then we should probably draw this one with a bigger arrow indicating it's got more polarity to it. So we could draw the dipole moment by drawing an arrow going from the one that's the least electronegative pointed toward the one that is the most electronegative. All right, and in which case this molecule's minus and plus would be like this. This molecule's minus and plus would be like this. Has a plus and a minus end to it. All right, this molecule doesn't have any plus or minus end to it. Now, molecules themselves can have polarity. That is, they can have a plus and a minus end to it, and how that works out kind of depends on the geometry of the molecule. All right, of the molecule. All right, which we'll have to talk about a little bit more later as to the shape of the molecule. We talked a little bit about the fact that water is bent, but then we have some other shapes too as well, and we'll talk about that a little bit later. All right, since the atoms of the molecule do not share electrons equally, like in the case of water here, we end up with a negative end where the oxygen is and a positive end where the hydrogens are. It's got a plus and a minus end to it. Now, if we have a molecule like this one here, methane, the sharing of electrons between the C's and the H's is not equal, but we have kind of a symmetry on both sides that sort of can cancel out the plus and minus stuff there. So you have to have kind of an imbalance of symmetry on the molecule in order for it to be polar. So methane is not polar. All right, carbon dioxide. Now this is just two atoms hooked together with a double bond, and again, oxygen and carbon don't have the same electronegativity, so it would be polar. But when you put carbon and oxygen together in carbon dioxide, then you have an imbalance between these, but the effect is kind of canceled out. So that molecule ends up not having any polarity. Now, why does this matter? Now, in the case of water, water is very polar. It's got a plus and a minus end to it. All right, a water molecule. So it can attract to things like ions. So when you throw an ionic compound into water, the water molecules grab those ions and pull the compound apart, and they just sort of hold on to the ions. Whether they're plus or minus determines what end of the water molecule they actually will attract to. Now, if you had two substances that were not polar, then they could dissolve into each other. All right? If you have two substances that are quite different, like one is polar and one is not, then it's likely that those two things won't be able to mix. That is why when you put oil into water, it sits on the top. It doesn't mix in, because oil is nonpolar and water is polar. So in order for them to mix, they have to kind of both be the same thing. They have to either both be polar or both nonpolar. If you mix different kinds of oil together, and think of the different oils they have, like in the kitchen. You have vegetable oil, olive oil, you got motor oil for cars. If you mix oil together, they would probably mix because they're all nonpolar molecules. But if you mix a polar with a nonpolar, then they tend to not mix very well. Now, when you have something like oil or grease on your hand, washing it off with pure water doesn't really work very well. And that's why you need to have soap, because soap is going to help the water molecules be less polar, and it can dissolve stuff that is nonpolar then. So putting soap into water helps you wash things like grease and things like that off of your hands. All right. If you've ever gotten like tree sap on your hand, it's a very nonpolar substance. So water does not take it off very well. Soap might help, but you need to have a nonpolar solvent, something like turpentine or gasoline, and then that can take the tree sap off of your hand. You could also just put soap straight on the tree sap and sort of rub it around, and that might dissolve into the soap, and then you can wash away the soap with the water too as well. All right, so polar molecules tend to dissolve into other polar molecules as well. So we sometimes use the like dissolves like acronym or hint that two things that are both polar can dissolve in each other, and two things that are nonpolar can dissolve into each other. All right, later we'll talk about what solvents are and solutes. The solute is the stuff that gets dissolved, and the solvent is the stuff doing the dissolving.